In Chapter 11, we're ready to run some tests between two samples. Now, having two samples makes some of these equations, or all of these equations, a little more cumbersome. But once we get familiar with them enough, they're really just as simple as Chapter 10. There's just plugging in the various numbers into the equation. Now, what remains difficult is in step 3 here in Chapter 11, we have more questions to answer. There's a larger tree that we need to select from as far as which test statistic applies to which scenario. In Chapter 10, there was just that one main question: do we know the population standard deviation? Here we have that same question, but then we have further questions beyond that. So we're going to start with an example where we answer that first question. We say we do know the population standard deviation. And so we'll walk through this more basic example where we work with, as we should expect, when we know the population standard deviations, right? There's two of them here. So when we know the population standard deviations, we're working with the z-score. Okay, so let's talk through an example. Now, we've been talking about two sample tests and all the extremely important scenarios in which it can be applied. Of course, when you're arguing about it, there's nothing more important than defending your favorite athlete. So let's talk about an example where maybe you want to support and argue for how good your favorite player, Byron Buxton, is. Okay, the Twins center fielder. You've been a fan for a long time, and how do you keep him? He's up and down. Okay, he's more hurt than not. That's mainly the issue. But how do you argue for his stardom? You probably talk about his speed, and one thing you might want to argue is that he's faster than, say, one of the all-time greats. Okay, arguably one of the top players of all time, and someday may finish as the best player of all time, Mike Trout. So can you argue? Can you justify that Byron Buxton is faster than Mike Trout? Well, we're gonna run a two sample test to test this. So let's set up our null and alternative hypothesis. So we'll work with the null hypothesis that they are the same speed. Okay, and there's a lot of different ways we could quantify speed. We're going to talk about kind of their max effort speed. And so we'll say kind of the mean speed when they're giving full effort, is that the same? Okay, our null hypothesis will be that is. And then if we reject that, we'll go with the alternative that one of them is faster than the other. Okay, so before we get into our test statistic and sampling, we do need to settle on a level of significance. Now, let's hold ourselves to an alpha of 0.1, a little bit lighter or lower of a threshold than some of the other, when we're doing medical testing. Probably if you're doing this, we might set this at 0.5 if you really just want to argue. But let's stick it at 0.1, and we've already said that we are going to know the population standard deviations, and so we're going to go with the z-test. Okay, so our z in step 3. Well, so step 3 is the z-test. Now, in step 4, what is our decision rule? Well, pretty straightforward here. We're going to be looking for a z, either plus or minus or beyond 1.645, right? So you can verify that on the z-table, but at a 10% level, that's probably sinking in now as kind of a defining value. And so we're ready to take this sample. Now, I've pulled up some data of their sprint speeds. And I have the following information. So we're gonna treat the sample. I don't know if I said this already, but one of the times where baseball players give max effort, or we can assume they're giving max effort, is when, for instance, they've hit a ground ball and they're sprinting to first base. Right? If they beat the throw, they get a hit. they get a hit, their average goes up, they make a lot more money. So you can be pretty sure that they're giving maximum effort when there's a close play. Okay, and so we actually have data for that, and we can take a look at it. So this is data from Baseball Savant. You can go on and find all kinds of fun stuff. And I went back to 2019 simply because in 2020 there were so few games played that it was, let's look at a larger sample, basically. Okay, so we're going to treat the sample as every time in 2019 that they gave max effort sprinting to first as a way to measure to estimate the population, right? We're after the population, which is all the time that they are sprinting max effort. Let's look at this sample. So we have the following information. So Buxton, the sample size was 52 max sprints to first base. We have an X bar in those sprints of I almost wrote that down wrong, 3.99. And sorry, I'm just making a couple little edits here. Okay, and we have let's say we know that the XB, that's not an X, the sigma B, the population standard deviation for Buxton is 0.15. For Trout had 30 sprints with an average speed of 4.29. Whoop, that's not how you write that. 4.29 and a standard deviation of, let's say he's a little more consistent at 0.1. Okay, so do we have enough evidence to reject the null hypothesis? Well, we're ready to plug this into our Z calculation. Now the Z, remember in this case is going to be, let's just write it down here. We have Z X bar T, X bar B minus X bar T over, this is, you know what, let's use the more space over here. Okay, so for our Z calculation, we're going to look at X bar B minus X bar T, right? So this is the distance between these two values. A little bit different. There's two moving parts, right? A little different than chapter 10, but there's two moving parts. The two moving parts means this standard deviation down below gets more complicated. But we've said that we know sigma B and sigma T. And so all that's left to do is plug these in. Okay, and we said 3.99 minus 4.29 over the square root. I have an error here, so these should be squared. Okay, so a little adjustment on the way to getting to that standard deviation. We're really taking the square root of the variance. So apologies for that. So this becomes 0.15 squared over, what did we say, 52 plus 0.1 squared over 30. Now, so this becomes negative 0.30, I think, up top. And so what does this simplify down to? I believe, and you can double check my math, this is 0.0277 roughly. And so when we finalize this out, it becomes negative 10.84, give or take. And so this Z value is well within our rejection region. And we have found enough evidence for you to support the idea that the null, or to reject the null, I should say. And yeah, so we can probably say that Byron Buxton is faster than Mike Trout, at least in their current stage of career. And so, yeah, so here, that's just a simple example of walking through, the Z calculation. Again, this is the most straightforward case. As we turn to some of the t-tests, we'll have to contend with degrees of freedom and all of that. But again, the whole process remains the same, steps 1 through 6.